of course, we are not going to do that. We are going to do a very simple case of, we are going to assume that we have looked at cases where I have a particle that was settling, right. Now we are going to take a case. I am going to say that now I am going to assume the aggregates to be still spherical. Okay, and now this spherical aggregate it has particles, and we said that the properties of the aggregate is typically in between the properties of the fluid and the particle, right. In that sense, we basically defined a quantity called rho aggregate, which basically goes as rho of the particle into 1 minus epsilon, okay, plus rho of the fluid into epsilon, right. Epsilon is something called as a liquid fraction, right. If I have this particle, there are solid here, and there are some vacant spaces, right. So epsilon is basically the volume of liquid in the aggregate divided by the total volume of the aggregate. Okay, that's your epsilon. Okay, that's a volume fraction of the liquid in the aggregate. Similarly, I can also define the solid fraction, right. So phi p, if I say solid fraction, this is a volume of the solids or the particles in the aggregate divided by the volume of the aggregate, right. I can define that, and they are related by the fact that your is 1 minus epsilon, right, because your phi p plus epsilon should be 1, right. The total fraction of the solid in the aggregate plus the total fraction of the liquid in the aggregate should be 1, right. Now and we said that we are going to take a case of a impermeable aggregate. We said we are going to take a case of a impermeable aggregate, and for that, so basically there is no exchange of fluid between the aggregate and the fluid, right. In terms of so what that makes is that I can still assume, if I what it basically means is that if I go back to this case, right, if I assume that the aggregates are impermeable, okay, so I don't have to worry about this fractal dimensions and stuff like that, because of the fact that your AP is a projected area, right. Okay, now if I, instead of a solid sphere settling, I am going to assume that there is an aggregate that is settling, okay, and if I have some way of measuring the diameter of the aggregate, okay, and the projected area that would still be pi d aggregate square divided by 4, right, by pi d square by 4, right. So therefore, what I can do is I can actually, whatever expression that we developed for some of the settling regimes that we talked about, right, g dp square rho p minus rho divided by 18 mu, this was for an isolated particle that was settling. I can actually use the exact same formulation, that is ut aggregate now is going to be g d aggregate square into rho p minus rho divided by 18 mu. Again, this is for the case of isolated aggregates, right. And I gave an example as to why I could still go ahead and use the Stokes settling expression, because if I take, like, say 15 nanometer particle, okay, I said if you make even an aggregate which is say 500 nanometer in diameter, if I do that, I said the fact that the particles, the aggregate that you are getting is still in the in the nanometer size range, your Reynolds number, if you calculate, right, REP would still be much less than 1. Therefore, I could still go ahead and use this, so this is where we had stopped yesterday, right. Of course, what I can do, of course, this is not rho p, right, this is rho aggregate, right, this is rho of, it's not rho p anymore, right. So this is a density of the particle. In this case, this is going to be rho of the aggregate, right. And we said, because I know that rho of the aggregate can be expressed in terms of the density of the fluid and the particle, you can write this as ut aggregate is equal to g dp square into rho p minus rho, okay, into 1 minus epsilon, right, divided by 18 mu. That's where we had stopped yesterday, right. Okay, so now I want to simplify this further. Again, here, this is aggregate, right, this is a df aggregate. So if I want to simplify this further, what I can do is I can actually take so your volume of the aggregate, okay, is the number of particles in the aggregate multiplied by the volume of the particle plus the volume of the liquid, right. Is that okay? So, all I am doing is you have a aggregate of certain volume, okay, and that should be equal to the number of particles that you have in the aggregate multiplied by volume of the aggregate. This basically gives you the total volume of the solids in the aggregate, and this VL is the volume of the liquid that you have in the, right. So, now what I can do is this is pi d aggregate q by 6, right, and that is number of particles, and volume of the particle is say pi, okay, d particle, right. So, that is the the dimension of the particle that make the aggregate, right, plus the volume of the liquid. I could write this as the volume fraction, okay. I could write this as because I know, can I express this VL in terms of the V aggregate? I can do that, right. So, what I can do is I can basically write this as, if I say that 1 minus epsilon, okay, would 1 minus, so epsilon is the liquid fraction, right, 1 minus epsilon is the solid fraction, right. So, therefore, if V AGG multiplied by epsilon would give me what is the volume of the liquid, right. Yes, no, yeah. So, therefore, what I can do is I can write this as pi by 6 into dp cube plus epsilon times pi dp cube by 6 into sorry, d aggregate cube into, that is it, right, that is the, let me just check, yeah, is that okay? So, therefore, what I can do is, so this gets cancelled, right, your pi by 6 gets cancelled everywhere. So, therefore, I could write this as, I can d aggregate power 3 into 1 minus epsilon is going to be Np into dp cube. Therefore, I could write this as d aggregate is equal to Np to the Np by 1 minus epsilon to the power of 1/3 into dp. Is it okay? So, therefore, I am able to express the diameter of the aggregate in terms of the number of particles that you have in the aggregate times the volume fraction of, so your epsilon, which is the void, people also call it as fraction of the liquid, people call it as voidage and things like that, and dp is, that is the diameter of the particle, right. Let's think about the limiting case, right. We just said that UT aggregate goes as G d aggregate square into rho p minus rho into 1 minus epsilon divided by 18 mu, right. Now, if I take the limiting case of your, what can you say about limiting case of epsilon going to 0 or your phi p going to 1, okay. In that case, if I look at this expression, your VL is 0, right, and your number of particles is going to be 1, right. So, what I am trying to say is that this expression that we have, it kind of becomes your single particle settling velocity, right, because your epsilon is 0, therefore, this term goes, right, number of particle is 1 here, okay. Therefore, your d aggregate is basically same as d particle, right. So, essentially, I mean whatever formalism that we wrote up here, that is extending whatever that we had for single particles to aggregate, it does seem it does make sense, because I am able to recover that limiting case of single particle settling, okay. Now, what I can do is I can actually substitute for d aggregate in terms of this quantity, right, into the settling velocity expression. Therefore, your UT aggregate would go as G into, instead of d aggregate square, I am basically going to put up Np divided by 1 minus epsilon, right, to the power of 1/3, okay, right, that is what I had, into dp, okay, whole square, right. And of course, there was rho p minus rho, and there was 1 minus epsilon divided by 18 mu, right. That is what you had. So, therefore, this goes as g into np to the power of 2/3, right, and I have dp square, right, and there is 1 minus epsilon, okay, and that is to the power of 2/3, right, minus 2/3 plus 1 because that is in the denominator, right, and there is a 1/3 power here and there is 2 here. Therefore, if I take it up, it becomes minus 2 by 3 plus 1, okay, and of course, you have, okay, and that multiplied by your rho p minus rho divided by 18 mu, okay. Therefore, if you simplify this, it becomes g dp square into rho p minus rho divided by 18 mu into np to the power of 2/3 into 1 minus epsilon to the power of 1/3, okay. And therefore, that is a single particle settling velocity, that is your ut itself, okay, times np power 2/3 into 1 minus epsilon to the power of 1/3, okay. So, what you are able to do is, I mean, of course, this is a very simple formulation. You are able to express the settling velocity of the aggregate in terms of the settling velocity of the individual particles, and and this expression does make sense because you know that as the number of particles becomes larger and larger, of course, your settling velocity has to go up, right. That is what it basically captures, and it also turns out that it basically also depends on the porosity of the aggregate, okay. If you have some way of measuring the number of particles in the aggregate, and if you have some way of measuring what is the porosity of the aggregate, you can basically go back and look at this equation and have a way of calculating your settling velocities, okay. But in terms of making particles of the aggregates of this kind and then doing settling is very hard, because first of all, making aggregates of controlled size is very difficult, okay. And even if you are able to make it, can I make aggregates of that look exactly identical, right? Because somebody was asking a question yesterday, if you have aggregates of different sizes, okay, then it again is more complex, right? First of all, working with aggregate, a single aggregate itself is tough, because your AP is different, porosities, all of that, right? But now if I have a collection of such aggregates of different morphologies, so it becomes very hard to kind of solve this problem. But there is a lot of interest in looking at settling of aggregates, because this is very much important in the case of applications, right? I said that in the case of water purification, or you look at any other lot of colloidal processing, when people do, you add additives to make aggregates, and then the way they behave in a fluid is important in the context of applications, okay. So that's about I just want to give you a kind of a heads up as to how does one think about if you have, instead of a nice spherical looking particle, if you have complicated objects like this, how does one look at aggregation, okay. That was the intention, okay. Now we are going to look at any questions so far. So we will look at start looking at multi-particle systems, okay. Okay, so I'm again going to draw the classic picture. So I have a column, okay, or maybe like say I have a container, and say that I have one particle that is in a fluid, okay. Say that your fluid is stagnant, right, okay. That's again I'm going to write the same formula, right. Now say that I'm going to start working with multi-particle, okay. I'm going to put another one, right. If I go on increasing the concentration of the particles in the system, can I again use a similar formalism that we had for single particle settling, okay. Any thoughts? Do you think that whatever formalism that we have had for the single particle settling, okay, can it be used for a multi-particle system? Yes, no? It turns out that you can still use it, but under certain conditions, okay. If you are working under very dilute condition, if the distance between the particles in the fluid if it is approximately 10 times the particle diameter, okay, and if the distance between the wall and the particle, if it is again approximately 10 times the particle diameter, it turns out that you can assume the particles would still be kind of flowing in a fluid in a very similar way as a single particle flowing, okay. And this is something called as a free settling regime, okay, something called as a free settling regime, okay. Even though there are multiple particles in the system, the behavior of each particle, okay, or one particle doesn't have any influence on how the other particles would settle, okay, or the presence of the boundaries of the container does not influence in any way how each of the particles would kind of behave in the presence of an external field, okay. And that is what is called as a free settling regime, right. Now, however, if, and as I said, right, a typical, you look at any system, right, I talked about viscosity measurements, right. When people talk about viscosity measurements, I said that there are something called as a rheometers, and I said that there are different geometries, right. I talked about parallel plate geometry, cone and plate, and co-ed geometries, right. When people and in all these measurements, what people do is people typically maintain a gap, right. There's a gap between two like say plates, for example, and one kind of comes up with a question is what is the gap that I should maintain, okay. And even in such cases, a typical rule of thumb is that you should ensure that the gap between the particles is at least about 10 times the dimensions of the object that you have in the fluid, okay. That means if I am working with like say 10 micrometer particle in a fluid, and if I were to put them between two plates, and if you want to do rheological measurements, the typical rule of thumb is that the distance between the plates has to be at least about 10 times the particle diameter, okay. In that case, I would at least maintain a gap that is more than 100 micrometer, because the particle size that I am working with is 10 micrometer, right, okay. Therefore, the similar kind of things also kind of works in the case of your free settling cases, okay. As long as the distance between the particles is larger than 10 times the particle diameter, okay, that's when you have this free settling, okay. Now, when you go on adding more and more particles into your system, okay, what will happen is that now as the particles come down, okay, it is going to displace some fluid, right. So I don't have this case of a quiescent or a static fluid anymore, okay. The liquid is going to go up, right, because as the particles come down, it will displace some fluid, and that fluid is going to go up, okay. And the drag for single particle doesn't apply anymore, because the fluid around the particle is also going to be in motion, okay, right. So therefore, you would have to think about kind of modifying whatever formalism that we had for the single particle case in terms of using it for the multiple particle system, okay. And so when the motion of the particle is kind of influenced by the wall or the other particles in the system, people use a term called hindered settling. Okay, when you have a large number of particles in your system, okay, if one is coming down, if there are other particles which kind of influence the drag that the particle experiences, okay. So in such cases, you say that the settling is occurring under what is called the hindered settling conditions. And what people have done is people have come up with some very simple kind of empirical relationships, okay. What you're looking at is a case, this is US is something called as a hindered settling velocity, okay. That is the settling velocity in the multiple particle system, okay. And it goes as the settling velocity of the single particle, that is under, this is under free settling condition, this is under hindered settling condition, and that depends on epsilon, which again is the fraction of liquid in the suspension, okay, or a slurry, right, okay, and this n is an exponent, and that depends on the again the flow regime that people work with, okay. If I take like say a limiting case of this very low Reynolds number, okay, typical value of n is about 4.6, okay, that is for Stokes settling regime, okay. And if you look at a typical case for Reynolds number that is about of the order of 1000, that is your Newton's settling regime, it turns out that the value of n is of the order of 2.5. Okay, people have kind of done a lot of experiments, okay, and they've kind of come up with this empirical relationship that the settling velocity under hindered settling condition basically goes as the free settling velocity multiplied by some function epsilon to the power of n, where epsilon is the fraction of the liquid that you have in the system, okay. Yeah. What is it, n that I calculate? Correct. So you're talking about here, right? Okay. So before I comment on that, what can you say about the settling velocity under hindered settling conditions? Do you think it will be lower or larger than? It's going to be lower, right? Yeah, it's going to be lower. Okay, therefore, I would still be under the. So if I were to say that I'm under the. So typically, if you look it up, let me just do it. In one of the examples, we have a case where we kind of calculate, okay, the free settling and hindered settling velocities. Of course, it is slowed down, but not by a large. Okay, so in that context, I mean, whether you take so UT here or US is not going to shift your Reynolds number by a large. Okay, maybe we'll comment on it when we do the. Okay, so now I just want to think a little bit about how do we get this. Okay, so as I said, this is people have done a lot of experiments and they've kind of come up with this empirical relationship. It turns out that you can actually derive it. Okay, so that's what we're going to do for the rest of the class. Again, starting point would again be assuming a certain settling regime. I can work it out by assuming that the particle settling in Newton's regime, or I can basically consider the Stokes regime. So starting is going to be again this equation, right? Now I have this equation, okay, and I say that this is applicable for Stokes settling velocity, Stokes settling regime, okay. Now because I said that your settling velocities under hindered settling are going to be lower than the settling velocity under free settling conditions, if I calculate the Reynolds number, it will turn out that your Reynolds number for the hindered settling condition would still be in the Stokes settling regime, right? So if I say that, look, I can take this expression and I can modify it for the case of hindered settling, what do you think should be the modification? So if I go back and look at the settling of the aggregates, right? I said that, look, I want to use the same expression, but I want to look at aggregates. I said that I would have to change dP into d aggregate. That's what we did, right? And I said you change your rho p into rho of aggregate. That's the modification that we did, right? Now if I want to again use a similar concept, but I would like to modify this for the settling in the hindered settling regime, what kind of modifications should I do for this expression? Yeah, one has to worry about these interactions, but you can still, I mean, I don't have to go for I mean, so what he's trying to say that if I have a dispersion of particles, say that case 1, case 2, in case 1 you have, like say, neutral particles, they are not charged, and I take case 2 where I have exactly identical particles, same number of particles in the fluid. In the case 2 there is a, you know, electrical double layer interaction, there is a repulsion between the particles. You know, the question is the settling in this case and the second case, are they exactly identical? Okay, so you can, it turns out that, you know, I can club all of this into some effective parameters. I don't have to really worry about, you know, the interparticle interactions. I don't have to worry about the charges and the van der Waals forces, everything. I can still use a similar expression, but instead of using the properties of the fluid, okay, I would have to use the properties of the suspending medium. Sorry, okay, let me just say what I mean. Okay, all you have to do is, now we said that your rho I was going to take as rho of aggregate in the settling of aggregates, right? Now that, you know, I have a fluid, now it's not rho p, right, your rho, right? Your rho is the density of the fluid that is in which the particles are embedded, right? Now what the particle effectively sees is not just the fluid, but the fluid plus the particles, right? In that sense, what I have to do is my now rho, okay, which is the rho of the fluid, okay, right, or rho of the suspension, okay. So what I mean by that is, instead of using rho, which is the density of the fluid, you would have to use the rho of the suspension, okay. Therefore, one of the modification is your g dp square into rho p minus rho of the suspension divided by 18. Now your mu, right, in the case of single particle settling, mu is the viscosity of the fluid, but now I have a fluid plus the particles. I would have to worry about not mu of just the fluid, but mu of the particle filled system, right? Therefore, the modification that I am supposed to be making is two modifications. One is you replace rho of the fluid with rho of the suspension, or the slurry if you want to call it as, okay. The other modification is that you replace your mu with what is called the mu effective, okay, which is the viscosity of the, not the just the fluid, but the particle filled fluid, right? And we kind of had an example in the previous class where we looked at, you know, how does the viscosity change as a function of maybe like say shear stress or shear rate, right, as a concentration of particle, right? So we said we had a case where, you know, the particles, the addition of the particle, you know, did increase the viscosity, right? If you have phi is equal to 0, add a little bit of particles, the viscosity goes up, right? In general, the viscosity is known to increase with the addition of the particle. Therefore, your mu should be replaced with mu effective, where mu effective is the viscosity of the particle filled fluid system, right? So therefore, your ut, okay, now we are going to call it as ut relative, okay. I'll come back in a minute as to why we call it as ut relative, is g dp square into rho p minus rho of suspension 18 mu effective, right? Because, you know, I don't have to worry about particle sizes, right? Because, you know, I'm assuming that, you know, you have a lot of particles, you know, when you have multiple particle system, you know, your dp is exactly same, right? Unless I'm making the particles cluster together, you know, unless I'm making the particles larger by aggregation, I would have to worry about, you know, changing this. But the fact that, you know, the particles remain as individual units and they continue to settle, so I don't have to worry about this. So I'm going to keep it as the same, and then I'm going to change, you know, this and this, right? And as I said, this mu effective, right, it is typically written as mu times some function, okay, and this function f of epsilon is typically greater than, it should be less than 1, right, because the mu effective is typically larger than the viscosity of the fluid itself, right? So therefore, and your rho, which is the rho of suspension, I can write it as rho of suspension, I can write it as rho of the particle into again 1 minus epsilon plus rho of the fluid into epsilon, right. I can again similar formalism, right. The density of the dispersion is basically, you know, some kind of a average of, you know, the kind of contribution that comes from the particle and the contribution that comes from the fluid, right. So if I substitute these into this equation, okay, it turns out that your ut relative, okay, would go as g dp square into rho p minus rho, okay. I had rho of suspension, right, divided by 18. Your mu effective, it becomes f of epsilon here. If I work it out, it becomes g dp square into rho p minus rho into epsilon into f of epsilon divided by 18 mu. That is your single particle settling velocity, that is your ut, right. That is your ut, okay, into epsilon times f of epsilon. Okay, I am going to put T here because that is going to be again terminal, okay, terminal velocity. Okay. Now we are going to, so therefore your relative terminal velocity under, okay, the hindered settling conditions, okay, when you have multiple particles in the system, basically goes as ut, which is the velocity and, you know, terminal velocity under free settling conditions, times epsilon, which is the fraction of the liquid that you have in the dispersion, multiplied by some function f of epsilon. We will talk a little bit about what this function is, you know, maybe in the next class. Okay, I will just stop here. If you have any questions, I will take them. Otherwise, we will meet tomorrow at 1 o'clock.